Hello everyone, welcome back to another lecture of COP-3402. Today we're going to be talking about how we can use pipes in our C programs to enable inter-process communication. So first of all, let's recap what a process is. So a process is a running program, a program in execution. This is an abstraction provided to us by the operating system. The operating system maintains the data of processes in what are known as process control blocks. Also task structs, what they are called in the implementation of the Linux kernel. And what these enable the operating system to do is to suspend a process and resume its execution later in order to provide the illusion of multiprocessing and concurrency. This concept is known as time sharing. So essentially we are virtualizing CPUs. Another thing to note about processes is that they have access to standard I/O, standard input, output, and error. This is another useful abstraction because it enables us to modify the inputs and outputs of a program without changing that program's source code. So if we have a C program, for instance, that prints hello world, we can redirect that C program from the shell to print to a file instead of to the terminal output without having to change the underlying C code. If we are running programs from the shell, then the shell opens standard I/O on behalf of the program when we run it from within the shell. If we are using the fork syscall from within one of our C programs, then those child processes will inherit any open file descriptors from the parent process. So if the parent has standard I/O open, then the child processes will have those same file descriptors open as well. Now, one potential shortcoming with processes is that they are isolated and inhabit separate memory spaces. So how can we actually enable these processes to communicate with each other? Well, one technique is to use signals, which we are not going to be discussing in this lecture. Rather, we're going to be focusing on using pipes. So a pipe, if you use the pipe syscall, just creates two file descriptors, a write end and a read end. So I have a diagram here to show this, very simple. To start off, if a pipe has a write end and a read end, similar to plumbing, I suppose, where you have data coming in and data coming out. Instead of water, it is data. This enables processes to communicate with one another. Now, what this enables us to do is to string together commands from the shell at without touching any C code yet. We'll look at the high level of what this enables us to do. So if I scroll down here, you'll see there's an example I prepared. Let me make this full screen, zoom out a little bit. You can see if we were to call find and pass the outputs to grep, so let me actually hop over to a terminal window here. Well, maybe I'll make this side by side with this diagram so we can see both at once. If I were to run find in my user bin directory, which will find all the files in my user bin directory and print them out to the console, and then use a vertical bar pipe to pipe these outputs to grep for the word zip, what we'll find is that grep will read the output of find. So this diagram here is showing that standard out is connected to the right end of a pipe, and the read end of the pipe is connected to grep's standard in. Grep will read the standard out of find for any words that contain any lines that contain the pattern zip. And again, it prints the results back out to the terminal. And we don't have to stop with only one pipe. We can connect as many pipes as we want from within the shell. Well, technically there is a limit. I'm not sure what it is, but there is a limit. So if I were to scroll down here, you can see the next example. And I can actually run this. So in here, we're going to connect the standard out of grep to another pipe's write end, and the read end of that new pipe to the standard in of WC. So if I were to pass this here with the -L flag to print the number of lines in output, you'll see we get 24 lines. And if I were to run this without WC, I bet that if I were to count these lines, it would equal 24 lines. Let's go back to the slides now. So how do we create these pipes? Well, we use a syscall like we've been reviewing so far in this class. Many of the operations you can do at the shell, you can recreate within C using system calls. So the syscall we'll be reviewing today is the pipe. So I'm going to go back to the terminal here. I'll make this full screen and then we'll look at the man pages for pipe. Section 2 of the man pages specifically. So the pipe system call returns an integer and expects a 2 an integer array with size 2 named pipefd as its argument. Let's read the description. Pipe creates a pipe, a unidirectional data channel that can be used for inter-process communication. That follows from what we've discussed so far in the lecture. The array pipefd is used to return two file descriptors referring to the ends of the pipe. Pipefd0 refers to the read end of the pipe. Pipefd1 refers to the write end of the pipe. Data written to the write end of the pipe is buffered by the kernel until it is read from the read end of the pipe. All right, that's all we need to know for now. Maybe one more thing to note here is just the return values for errors. So on success, 0 is returned. On error, -1 is returned. Error no is set to indicate the error, and pipefd is left unchanged. So as in most cases, when using system calls, check for -1 as a return value. Now let's see a basic example of pipe in action. So I'm going to open a window here. Let me actually open this in tmux so I can split my screen vertically. I'll open this example I have, which is called pipe.c. On my right-hand side here, I'll compile my code when it's ready. Maybe I'll just close this window for now. And what we have here is a message we are initializing to the string hello world. We are getting its count using the string length library call, and we are creating a buffer for storing a result for later on. The first thing we do is create a pipe. So actually what I'm going to do here is go back into the slides on the left-hand side here and go back to my diagrams here. And I'm actually going to draw what is going on in this diagram as we are reading the code. So at this point, we are creating a pipe. I'm going to snatch one of these pipes from up here, copy and paste them in down here. And what pipe will do is create two new file descriptors, assuming it succeeds. So I'll drag this down just a little bit. And I'm using this variable pipefd to store these new file descriptors. So maybe I'll just create them here like this. So pipefd0 for the read end of the pipe, pipefd1 for the write end of the pipe. And to make things easier on myself, because I don't want to have to remember these magic numbers, I've created an enum here, which is basically a integer constant, a compile time integer constant, a named integer constant, where read is equal to 0, write is equal to 1. So what we're going to do, what I will do in this diagram here is change the 0 out for the word read to make it clear that this is the read end of the pipe that we are referring to. Let me make this a little bit bigger. Drag these over. Okay. Then I'll change this to the right end of the pipe as well to match. Make it a little bit over to the left. Okay, that's good. Now, the read end of the pipe by default is going to be right here. I'll just draw it here to make it easier to see what's going on. And the right end of the pipe will point to the other end of the pipe. We'll point that over here. Let me draw that. Actually, it might be easier if I were to reverse this. So let me move this one down to the right end of the pipe. And I'll have this one be for the read end. So it goes left to right, which is how most of us read, I think. All right, so and let's go back to the code. On this following line, we are writing to the right end of the pipe. So we are using this pipefd write, and we're writing here, sending data to the right end of the pipe. We are sending the message, hello world, to the right end of the pipe. So maybe I'll draw that out. Hello world \n is going to the right end of the pipe here. And we're sending count bytes because that's how many bytes are in the hello world string. Then we are closing that right end of the pipe because we no longer need it. So after we've sent the bytes through, you can imagine them as being in the middle of the pipe now. We can delete that right end of the pipe. And it's good practice to close your file descriptors when you are done using them, especially with pipes for reasons that we will explore later in this lecture. Afterwards, we use the readsys call to read a certain number of bytes from the read end of the pipe. And we are storing the results in that result variable that I declared earlier in this program. So conceptually what's going on here is the read end of the pipe is receiving the string hello world. And then when we're done, just like before, how we close the read end of the pipe, or the write end of the pipe, I'm sorry, we are also going to close the read end of the pipe. Now here, we've obtained the string hello world and it's stored it in the variable result. We will write the result to the console with a call to write passing standard out file no, which, in case you don't remember, is defined in user include unistud.h as just 1. So I'll run make all to compile all the examples in this directory here. And I will run this pipe example, and we can see that it works as expected, and the text hello world is printed to the terminal with standard out. Let me just verify that I am recording. Yes, I am. Excellent. All right, so let's see another example before we go on with the rest of the slides. Scroll down here. Pipe fork. So let's take a look at this one. Pipefork.c. So in this example, we are going to be using fork, where the child is going to be, well, the parent is going to be writing a message, and the child is going to be receiving it from a pipe. So to begin, we set up a string here for the parent to send to the child. Hello from the parent. We are getting the number of bytes in that message with the string length library call. And we are creating another variable result for storing our result. And again, we're using these enums read and write to make it easier to see what's going on with these, to distinguish between the two ends of the pipe. And here we are calling pipe to create a pipe. Notice that I have removed the checks for errors in order to make the code more concise for these examples. In your code, you will definitely want to include checks for -1 and emit the correct calls to p-error and exit on error. And again, because we are calling making the pipe, we get 2 new file descriptors. So I will draw those here. Let me move this down, give that a little bit more space. Copy these, that should be fine. So pipe fd read and pipe fd write. And again, the right hand of the pipe, we will connect it to the left-hand side of the pipe here, like so. And the read end of the pipe, we will connect it to the right-hand side of the pipe like this. Okay. Now in this example, after we create the pipe though, we then fork. So what is this going to do? Well, you might recall when we fork a process, the child receives copies of all the parent processes open file descriptors. So we are essentially copying all of these. And they're pointing to the same place though, so we can say the terminal is what these file descriptors point to for the child as well. And instead of pointing to a new pipe, they're pointing to the same pipe. So we can change these to point to the same pipe, the read end and the write end. Drag this over here. Maybe what I'll do to make this a bit clearer is change the colors as well. Change that to a different color. Let's say blue, dark blue. That looks better, I think. I'll make that dark blue as well. All right. And maybe, yeah, I should probably change this one as well. Change that to dark blue. Okay. So within the child process, the first thing we're going to do is close the right end of the pipe. So this arrow connecting the right end of the pipe to the child is going to be gone because we're not going to be using it, because remember the child is going to be reading from the parent. And then within the child process, we are going to read from the read end of the pipe in order to store the result in the result variable. Oh, you know what? I think I deleted the wrong line here, actually. It should be this line because we are closing the right end, not the read end. Got a little confused with where these arrows were connected. It should be right here. Try to make that a little bit more clear. There we go. That should be good. And then once we're done reading these results into the result variable, which I'm going to, what I'll do is drag this out here to signify that the result variable is in the child process. Then we will close the read end of the pipe, like so, because we no longer need it. And it's good close file descriptors you're no longer using. Result contains hello from parent, so what I'll do is copy this text over, yank it from Vim, paste it into here. And what we'll do next is, in this code on this line here, we are going to write to standard out file no, which again is just one. We will write that result to standard out, which will arrive at our terminal. But the way this text first arrives in the child process is through the parent process. So the parent process will first close its read end of the pipe because it is only writing. It never needs the read end. And then it writes the string hello from parent, and I'll make this one black to signify that it's coming from the parent. It sends this message through the right end of the pipe into the pipe itself with this call to write here. And once it's done, it closes the right end of the pipe because it no longer needs it. And as we just saw, the child would have read from the read end into the result variable and then print that out to the terminal. All right. So it's still not really clear what the purpose of these pipes are, why we would want to use them. So let's look at a more complex example, and that is to connect different programs together. So we were able to make a child and parent communicate with each other, but the results have so far been somewhat contrived. What if we wanted to connect two different programs to each other? Well, the general setup for this is to have one process be the master process and the children processes be the ones responsible for executing those programs you want to connect. So the master process creates the pipe and then uses fork and exec to execute the child programs and manages the std.io as necessary with the pipe. So again, just a recapitulation of this process here. You can view the slides for a review of this. We're going to be viewing a diagram now shortly with this example, and it's going to be called filter.c. So let's take a look at that file. So this should be familiar to you by now. We have our enum for specifying easy to read names for the read and write ends of the pipe. We declare a pipe variable. We make a call to pipe to create our file descriptors. And now let's go to the diagram since we're actually calling pipe. I'm going to copy this, paste it in here. So we have our pipe ready. And I'm going to drag this a little bit down, lower. And let's actually change this so that the standard out is clearly going to the same terminal as standard in. So again, we're going to use pipe fd read for the read end of the pipe. Drag this over for a bit more space. Try to get it a little bit centered. That looks better. And then we'll have pipe fd write be the right end of the pipe. And we'll connect these to the pipe as we've done before. So the right end is the left-hand side of the pipe. And the read end is the right-hand side of the pipe. So we read from left to right. Maybe it would be better if I flip this arrow around like this to signify that we're reading. And now the first thing we're going to do in this program is create a child process with a call to fork. So we're going to duplicate everything we have here to create a child process. I'm going to change the color of all this to a different color to signify that it's a child. We'll say blue. And again, this pipe here can be the same pipe. We can reuse that same pipe that the parent uses. So the right end of the pipe goes to the right end of the parent. Or of the pipe, I'm sorry, not the parent, of the pipe. The read end of this pipe, I'm sorry, this is actually incorrect. Let me fix this here. There we go, that's better. Oops. And the read end of the pipe should go to the read end over here. The pipe fd read file descriptor should point to the read end of the pipe. Struggling to organize this. If I scroll down a little bit, give myself some more space here. Better yet, why don't I actually just draw a new arrow for the read end and we'll connect it like this. I think that's better. Yeah, that makes more sense. Flip it around. There we go. And these are not using a different terminal, they're using the very same terminal that the parent is using, so I can draw these arrows here to signify that as well. Okay, so now that we have duplicated the parent process into a child process, the first thing we'll do is close the read end of the pipe. Because what we're trying to do is, again, I'll write this out in the code, execute this shell pipeline, ls to wc. So ls should still read from standard in, so we don't need to use the read end of the pipe because we're reading from standard in. So the read end of the pipe can be closed. We can effectively delete it. Now in this line we are using dup2 to duplicate standard out of this process to the right end of the pipe. So what we'll do here is effectively what dup2 does is delete the file descriptor for standard out, or close it I should say, and then reopen it pointing to the same file descriptor as standard pipefd write. The same file description I should say as pipefd write points to, which in this case is the right end of the pipe. Then, because we already have redirected standard out to the right end of the pipe, we can close the right end of the pipe now. And then finally, we can use exec-lp here to replace our child process with the program named ls, passing its first argument as ls, because that is the convention. When you call a program, you want to make sure its first argument is the name of the program itself, as it was called. And we pass null here to signify the end of arguments. We are using the p suffix of exec to specify that this exec call should look up program names in the user's path environment variable. And we are using the L variant to mean that we can pass these arguments directly to the call to exec here and not within a separate variable for storing program arguments. So to signify this, I'll just replace this name filter with ls. Now let's look at the next child. So this child, again, going to become a duplicate of the parent. So I'm going to select everything here, and I'm going to copy it over here. We'll change the color this time to orange, so it sticks out very much differently from the other child. And again, it's not going to be pointing to a different terminal. It'll be pointing to the same terminal as the parent, so I can draw that here like so. Might be a little tricky, but I think we'll manage. Oh, that seems to work. And standard out, likewise, is going to be pointing to the parent as well. Let's see if I can get this to work. It's kind of becoming a game to arrange all these lines. All right, that seems to kind of work. We'll keep it at that. Now the child also inherits the open file descriptors for the pipe, so what I'll do is delete this orange pipe here and connect the right end of this pipe for the child to the same right end of the pipe that the other processes file descriptors are pointing to. And the read end of the pipe is going to point to the read end of the, or pipefd, and the child is going to point to the read end of the pipe, so I'll connect that here. And I think what I'll do is, again, reverse the direction of these arrows. All right. And now that we've done that, the child process will first close the right end of the pipe because this right child, again, remember, I'm going to write this out again. What we are trying to do is ls pipe to wc. The right-hand process here is not writing to the pipe, it's reading from the pipe, so we can close the right end of the pipe in the child process. And we're going to redirect the child process's standard in to the read end of the pipe, so we will close standard in here, and then reopen it to point to read from the read end of the pipe. And after doing that call, making that call to dup2, we will close the read end of the pipe because we already have a file descriptor now, standard in, that reads from the read end of the pipe. Then finally, we will run exec-lp to replace this process with the WC program. And because we have not changed standard out for this process, it should write to the terminal when it is finished. Now, meanwhile, in the parent process, we are going to close the file descriptors we are no longer using. I will close these here to signify this. And then we will wait until the child processes are both finished by making 2 consecutive calls to wait. And we're passing null as the argument to wait because we don't care about the child statuses. We are only concerned with waiting until both child processes finish. And the call to wait, what it will do is, if I were to press Q-K here to open up the syscall command pages, the wait system call suspends the execution of the calling thread until one of its children terminates. So by calling it twice, we wait until both children have terminated. Now if I were to run this, make filter, and then run the filter program, you can see it successfully does the same thing as if we were to type in ls and then pipe the output to WC. So I'll run that again, just to be very clear. We have connected the ls program to the WC program from within our C code. Now one gotcha here that I would like to point out, a potential issue you might run into, is forgetting to close the open file descriptors in the parent. Now, you might get away with forgetting to close the read file descriptor. So if I were to run this with make and then run this program, you can see it still works. But if you were to forget to close the write file descriptor, you'll be in for some trouble. And let me demonstrate this. You'll see that my program hangs. It does not finish executing. So why is that? Well, let's go back to my diagram here and pretend we have not closed those 2 file descriptors. If you don't close the open file descriptors for a pipe, and especially if it's the right end of the pipe and you have not closed its file descriptor, and you make a call to read, which we are implicitly doing because this WC process, child process, is reading from the pipe, then that child process will not finish running until it's received an end of input signal from the pipe. And the pipe will not send that signal to WC until all of its open file descriptors are closed. And standard out, the ls program here will send that for us when it finishes running. The program will close and it will close its open file descriptors. The shell will close the open file descriptors for ls for us. But the parent process, since it is still active, unless we close these manually ourselves with those calls to close that we saw, I'll go back to them here. Unless we close these ourselves, the right end of the pipe will stay open, and WC will continue to expect more input, and will not finish running until we've terminated those ends of the pipe, essentially. So don't forget to close the right end of a pipe when you were using it. So again, we can just run this to make sure we've corrected the issue, and yes, it seems like we have. Now, that concludes the information about pipes. What I want to talk about now is an example of wait.c. This is something somewhat unrelated, but I think it's interesting to note another form of interprocess communication, which is signals. So I said we wouldn't talk about this, and I sort of lied. We are going to talk about it a little bit, but it's not really essential for this course, but it is interesting to know. So I'm going to open this wait.c example I prepared here. What we're doing in this example is declaring a value of PIDT, called PID. PIDT is the value that stores process ID types, process IDs. We're making a call to fork here, switching on the result, and we're storing the result of fork in this PID variable. If the result of fork is -1, then we know it is an error and we can exit with a failure message. We get the message from using p-error and we exit with exit failure, which expands to 1, a non-zero value, probably 1. Otherwise, in the child, if it's 0, that means we are in the child. We're going to use puts to print this message to the terminal window inside child process. I'll make that a capital I because I prefer that. And then we are declaring a variable called prog, which we are assigning to the full path to the user bin sleep program. A variable called newArgv, which contains the arguments for prog, or I'm sorry, for sleep. So remember, the first argument for a program we are running should be the path to that program itself as it was called. But the subsequent arguments are the actual arguments to the program. So here we are calling sleep with the argument 7, which means that when we exec this program here in the following line, this child process, will be replaced with a call to sleep for 7 seconds. So this execution of this child process will suspend for 7 seconds. And because exec never returns, if we do actually reach this line of code, that means there must have been an error. So we can p-error exec v and then exit with exit failure. Remember that we are using the underscore variant of exit because we are in the child process and we want to avoid accidentally triggering exit signal handlers or exit handlers attached with the add-exit syscall. So instead we use underscore exit to skip performing cleanup actions that the parent should perform. Not really necessary for this course to use underscore exit, but it's best practice to do that, so I recommend doing it. Otherwise, if we're in the parent, we will print the child's PID by printing the value of the PID variable, which should store the value of the child process ID. And we have this W status variable for getting the status of the process after calling wait PID here. So what wait PID will do is enable us to wait for a specific process to change state. By default, we wait for it to terminate. This could be by passing the kill signal, which I believe has value 9, or the term signal, which on my machine has value 15. And when we call this wait PID library, or system call here, we are also passing the address of this W status variable we have declared in order to get some information out of the reason of why this process changed state. And normally, again, wait PID only stores state changes that result in termination or a process being killed, but we can pass these options here with untraced and with continued to get information about when a process is suspended and when it has been continued, respectively. And this gives us another WPID variable. Let me actually open the man pages because I can't remember what this WPID means. Let's see. Look for the return value. On success, returns the ID of the child process whose state has changed. Okay, so this should just return the same ID of the PID stores because we're only checking if that process has changed state. And what we'll do in a do while loop, so remember do while loops execute once and then check their condition to see whether or not they should continue executing. The next thing we'll do in this do while loop is check what exactly happened to the child process, because if we pass this wait PID line, then execution has continued and the child has assumedly changed state in some way, had some signal sent to it, So if the child was exited with the W if exited macro here, we can check that. And then we'll print that the child was exited and extract its exit status with this macro here. If the child was instead sent a signal, and by default WIF signaled checks if the child was sent a termination signal, then we print the number of the signal that caused the process to terminate by using the W term sig macro here. So this could either be 9 or 15, whether the process was killed or terminated, depending on the signal used. And here we use W if stopped to check if the process was stopped by a signal, and if it is, we get the number of the signal that was used to suspend the process. And finally, if the process was continued, we use the W of continued to check that case, and then if it is, we just printf continued. When we're done, we will finish executing this once the process has either executed or has been sent the termination or kill signal, and finally exit with exit success. So let's make this example. What I'm going to do is open a separate window here, and let's try running this. So I can run wait, and you'll see we get the child's PID. We'll have that message inside child process. When the process finishes running after 7 seconds, you'll see we get that exited message with status equals 0. Now we can also run this process. What I'm going to do is actually prepare a call on the right-hand side here to kill. So kill expects you to pass a process ID, and it will by default send the sig term signal, the termination signal, to a process that, whose ID you pass to it. So I'll run this, and then quickly type in the PID of the child process, and you'll see it was killed by signal 15, the sig term signal. Now we can also kill the process with the 9 signal to truly kill it. This is the kill signal. And you can see now we have killed by signal 9. The reason why I might want to use 9 instead of the default 15 is because 9 cannot be overridden by programs and will assuredly kill them. Let's try this one more time. If I were to run this process with wait, and then pass the kill stop signal to 11744, I think this is correct. Oops, I was too late. What I can also do is just press Ctrl-Z to suspend the process, and then FG to resume it. You can see we get the message wait. Oops, let me actually run that again. Run wait, and then press Ctrl-Z to suspend the process, and then FG to continue it. You can see we get the message continued printed to the console, and then exited and status equals 0. And we should be getting the message that the process was stopped as well. Let me see if we can force that here. So if I were to run this program here and kill by passing with the stop flag, so you can use the names of these signals as well. So I'll say kill and send the stop signal to the child process. Let's run wait, quickly pass in the PID of the child process, 91, and we can see that it was stopped by signal 19. So we were successfully able to view that stop message. And likewise, I can also send the cont signal to continue the process, and now we get that continued message and the child finishes executing successfully. So that concludes today's lecture. I hope it was very informative, and I will see you all next week.